Good morning to all of you.
Good morning, sir.
Yeah, good morning. So, are there any questions, doubts? Anybody, any question, any doubt? Okay, so then let me start. So, yeah, we are continuing with the finite deformation. Okay, screen it is not writing. So is the screen visible?
Yes, sir.
Okay. Yeah, so yeah, I am continuing with the finite deformation. So last class we have seen the element level governing equations. So we said that element level governing equation the equation was integration over the reference volume V naught B plus BNL transpose into S, where S is second Piola Kirchhoff stress tensor, dV naught minus again integration over reference volume V naught H transpose into FB, capital FB in the reference configuration, dV naught minus integration over S naught H transpose into Tn ds is equal to a null vector. So yeah, this is where we left in the last class. So we got the element level governing equation like this, and we said that it is nonlinear. So now yeah, we want to solve this using Newton-Raphson method. This equation is solved using Newton-Raphson method. So for that, what we do is this equation we write in the incremental form. So the incremental form would be see S is an unknown function of elemental degrees of freedom through strains and strain in terms of strain displacement relation to displacements, and also this BNL contains the gradients of displacement, so that also contains unknown. So both the terms have to be accounted for. So when we write this, so we will have the integration over V naught, and then this B plus BNL I am writing first as it is, B plus BNL transpose, and then the derivative of S with respect to green Lagrange strain tensor. So this is the constitutive matrix, and then delta E, and delta E is written as B plus BNL into delta DE. So this again we get here B plus BNL, and then this integration is over the reference volume V naught, and this is evaluated at the previous iteration I, and then into delta D E I plus 1. This is calculated for the next iteration. Plus we will have this again the second, because when we take the incremental form, now the derivative term of the Taylor series expansion. So once we have taken the derivative of S, and we got these terms, and second time we also need to take the derivative of B and L, because that's an unknown function of displacement. So we will get this. Of course B is constant independent of DE, so its derivative is 0. So we will get this delta B and L, that is incremental form of this, and this is delta B and L actually is evaluated at current iteration, but S is taken at the previous iteration, SI dV naught. So this is one term we will have, and then of course the whole thing evaluated at the previous iteration. So whole thing evaluated at the previous iteration, we will have plus no, this term itself evaluated at the previous iteration, and these terms of course the externally applied loads. So this term would be integration over V naught B plus BNL transpose into S dV naught evaluated at previous iteration, and minus of course these terms. We will have H transpose into FB dV naught, minus we will have integration over S naught, the reference surface area, and we will have H transpose into Tn ds naught is equal to a null vector. So this is what we will get the incremental form of the equation after using the Newton-Raphson method. So now if you look at we basically assemble and solve this for delta D. So the equation now, if you look at no, I can write this equation in a short form. So you can say that this will be time, we will have tangent stiffness matrix KTE evaluated at the previous iteration into delta DE for the current iteration is equal to external load, and external load I'm just putting as FE because it has external forces which are known for that iteration, and you have some quantity which is evaluated at the previous iteration. So now here in this equation, where now this KTE I is nothing but integration over reference volume, this B plus BNL transpose into derivative of S with respect to Green Lagrange strain tensor. So it would be a 6 by 6 matrix into B plus BNL dV naught evaluated at previous iteration, this term, and plus we will also have the contribution coming from this one. So now you see S is known, which is evaluated at the previous iteration. So for previous iteration we know S, we would calculate strain in the previous iteration, and therefore we will calculate S from the constitutive relation. But delta BNL contains delta DE term, so that is also contributes to the stiffness matrix. So I am denoting here that by KGE, and I will define what this KGE means. So this is also evaluated at the previous iteration. So this is your KT consisting of these two terms, and of course this FE is now let me define FE and then KGE, and this vector FE is integration over V naught B plus BNL transpose into S dV naught. This is evaluated at previous iteration, and then we will have plus integration over V naught H transpose FB dV naught, plus we will have integration over S naught H transpose into T and ds naught. So this is the right hand side Fe, and this kg is written, no, this term, this particular term, this term, this term, it is written such a way we have to know multiply and then rewrite, so that we have a matrix and delta d on the right hand side. So that is written such a way that, no, this kg e into delta de is actually integration over V naught delta BNL transpose into S dV naught. So once you have got this equation, then of course you assemble the element level governing equations, impose boundary condition and solve it for delta D. So you will assemble element level governing equations, impose boundary conditions.
Sir, can you please explain that line again, sir? KG.
Yeah, so now we have, as I was saying here, we have got, no, this term delta BNL transpose into S. So we have to rewrite that, because delta BNL has got derivatives of shape function in it and also the gradients of displacements. So we rewrite this and it we rewrite in such a way that we have this in the form of a matrix Kg into delta D. So I think I will take some examples and I will clarify that how this is rewritten there. So assemble element level boundary equations, impose boundary condition and solve for delta D,
Sir,
and
in FE expression, I think there will be a minus sign at the starting.
yeah, that's right, yeah, actually this term is minus, you are right, this is minus, the first term is minus. Thanks for this correction. Yeah, so this is how no, you write this. So now let me take some examples on this. So simpler examples. This is what we have discussed as a general 3D case. So now if we want to, but no, as example, let me take the simple example, very simple example, linear elastic rod under axial load. So that is examples. So I am taking linear elastic rod under axial load. So that is what I am going to consider is a two-noded truss element. So the element is like this, that you have, it's a one-dimensional element, and this is the global x coordinate, and there is a load, distributed load here, which is Q, and this is node 1, this is node 2, and this length is small l, and there are, in addition to distributed force, there are concentrated forces at node 1 and 2, and the degrees of freedom are u1 here and u2 here. So this is the example we are considering. Only thing now we are considering that deformation gradient, that is in this case du by dx, is finite. So we need to consider the quadratic terms in the Green Lagrange strain tensor. Yeah, okay. So now you already know that for this case we write u in terms of the shape functions n1 and n2, into this u1 and u2, and where this is as it is as we do in the linear finite element formulation, and n2 is x by l. And now you can say that this is interpolation matrix H, and this is the vector of elemental degrees of freedom. So this is H and this is D. And then we need du by dx. So du by dx will be, of course, will be equal to dn1 by dx, dn2 by dx, that is you already know, into dE. Then if you look at the strain, now we are considering the x component of Green Lagrange strain tensor. So there is only one displacement, that is u, which is a function of x. So this will be du by dx plus half of du by dx whole square. So this is the Green Lagrange strain tensor. Instead of linear strain displacement relation, we are taking this nonlinear strain displacement relation. Now if you look at the variation of this Exx, so delta of Exx would be delta of du by dx, and plus the second term when you take, so it would be du by dx into delta of du by dx into 2. So 2 and half will cancel, so we will get du by dx into delta of du by dx. So we will get this term. Now if you look at the, we want to identify the B and BNL matrix. So we can see here that we can write delta of Exx is equal to, first will be from this term we will get actually B, which would be dn1 by dx, dn2 by dx, and into delta of u1, delta of u2, and plus now the second term if you look at, so this is delta du by dx, that we are going to write in terms of n1 delta u1 plus n2 delta u2, and this du by dx we will keep as it is multiplying term. So du by dx into, we will have here dn1 by dx, so this is first row column, and then du by dx into dn2 by dx is the second column, and then we will have delta u1 delta u2. So this is what we will have. So this is the first one is actually B matrix. So this is, I am denoting as B, and then this is this whole thing as BNL. So plus BNL and into delta DE. So this is delta DE. So you can write it like this. You can simply also write it as just matrix B plus BNL, both of them are matrices, into delta DE. So yeah, this is what we get as. Now if you look at the, because it is linear elastic and the the uniaxial state of stress, so Sxx, first P-alloy Kirchhoff stress tensor, no sorry, the x component of second P-alloy Kirchhoff stress tensor would be equal to Young's modulus E into Green Lagrange strain tensor Exx. So if you look at the derivative of Sxx with respect to Exx, that is simply going to be actually E. So I am directly, let me write the element level governing equation. So if B, only thing is S has got only one component, the second P Kirchhoff stress tensor. So the element level governing equation would be element level governing will be, now here the integration over volume we are splitting into area into integration over x. So then we will have integration 0 to L. L is the length of the element in the undeformed position. So this is the integration over the reference volume. A is the reference cross sectional area in the undeformed configuration, and then we have here B plus BNL transpose as it is, and S has got only one component, so I am writing just Sx into dx, and then minus integration 0 to L. Now you will have this H transpose into Q dx, and then you have this internal load vector which is Q1 minus Q2. Now this is equal to a null vector. So this is what you get as the element level governing equation. it's a nonlinear equation. We want to solve it using Newton-Raphson method. So we write its incremental form using Taylor-Sage expansion, as we did at the start of this lecture. So I can say that the incremental form using Taylor series expansion will be the way we did earlier. So again, I'm going to write in a similar manner, and then I will explain you how to finally write the final form. So we will have the first term, integration 0 to L, and then A, and then we have B plus BNL transpose, and then E, and then again we have B plus BNL. So the delta of Sxx and delta of Sx is written as E into delta of Exx, and delta of Exx is written as B plus BNL into delta D. So this is integration evaluated at the previous iteration into we'll have delta DE at the current iteration I plus 1. Plus we will have, as we said, the derivative, the gradient of this BNL. So the second term we are going to have again integration 0 to L and A, and into we will have delta BNL transpose into Sxx. Sx, this is
Sir,
evaluated at the yeah.
Sir, is Sxx a component of second Piola-Kirchhoff tensor, or is it
Yeah,
just
yeah,
stress?
it is a x component of second Piola-Kirchhoff stress tensor, and in this
Okay.
problem that is the only stress component which is non-zero.
Okay, sir.
All the other stress components are zero because it is a uniaxial state of stress. So this is evaluated at the previous iteration into Sxxi dx. So this is what you have, and on the right hand side we will have minus, and then integration 0 to L A B plus BNL. We are using simple Newton-Raphson as we did earlier into Sxx dx. This whole thing evaluated at previous iteration, plus we will have integration 0 to L and H transpose Q dx, and plus we will have minus Q1 and plus Q2. So yeah, this is what we will have now. As far as this term is concerned, now let's look at basically this term. So let me rewrite this again. So the first term we are keeping as it is. So that is integration 0 to L A B plus BNL transpose into E B plus BNL dx, whole thing evaluated at previous iteration into delta DE at I plus 1. So this is as it is. Now this term. So if you look at delta, no, BNL is defined over here. This is your BNL. So BNL has got this term du by dx and du by dx. So what we can actually do is we can take and we have to take the transpose of this. So instead of a row, it will become a column vector, and then this du by dx we take on the right hand side. So we will have column dn1 by dx, dn2 by dx into du by dx, and then du by dx we write as basically derivatives of the shape functions dn1 by dx and dn2 by dx into delta d. So that is what we are going to write that term. So what you will get is then this second term, this one we are writing integration 0 to L and integrate the area A, and as I said delta BNL transpose will become a column vector. So it will be dn1 by dx, dn2 by dx, and then we will have delta of du by dx. So delta of du by dx, finally we are going to write. So we will have delta of, let me write and then expand it, delta of du by dx, and this term is evaluated at I plus 1th iteration, and then you have Sxx which is evaluated at previous iteration dx. So this is what you will have this term is equal to right hand side. These things will come as it is. So no, three terms will be there as it is. So now finally, no, we can write this delta of du by dx as dn1 by dx, dn2 by dx into delta d, and delta d we can take as a common term. So we will finally have let me just write that. So first term as it is, this I am writing as it is. So integration 0 to L a b plus bnl transpose into E into B plus BNL. We have already defined that dx, and this whole thing is evaluated at the previous iteration delta D at I plus 1. And then the second term we are writing again integration 0 to L A and dn1 by dx, and then dn2 by dx. And then you have this delta of du by dx, and that would be written as dn1 by dx, dn2 by dx. And yes, since a single quantity you can write it anywhere, so you will have sx and dx, and this whole thing is evaluated at previous iteration. So basically this sxx is evaluated at previous iteration. Into will have delta de at I plus 1. So this is what you're getting, and this is what I referred as kg, a kge. So this is your kge for this, no, this is here kge matrix evaluated at previous iteration. So this is what you have, and on the right side is equal to those terms, no, integration 0 to L, we will have this a b plus bnl transpose into sxx dx, this whole thing evaluated at previous iteration, and plus the external loads 0 to L h transpose q dx minus no, plus minus q1 and q2. So this is the incremental form of the equation. So the kg matrix, so this is how you manipulate it and finally write in the form of a matrix and take delta d common. So see from here, no, we had du by dx into dn1 by dx, du by dx into dn2 by dx, and delta, then we take delta. So the unknown is du by dx, so you delta goes with du by dx, and then delta du by dx you write it as dn1 by dx, dn2 by dx, and delta de. So that delta d is coming over here, and so rest of the things whatever we have this inside matrix is a kg matrix. And why it is? Because it is depending, why it is known as, sometimes we call it a geometric stiffness matrix, because it is depending on the stress and then only the geometry. The material properties are not coming into picture directly, although sxx would be written in terms of material property E and the exx green Lagrange strain tensor, but directly it is in terms of stress, so we call it a geometric stiffness matrix. Now, yeah, so this is
Hello, sir.
yeah.
Sir, can you tell about that constitutive relation what you are using? Like, what is the
Yeah,
constitutive
so the
relation?
constitutive relation I have assumed here that it is linear elastic. So I am assuming that no, the of course the only non-zero component of second Piola-Kirchhoff stress tensor is this Sxx. So that's the only non-zero component, and that is equal to E into Exx. So for the uniaxial state of stress, that is only Sxx being non-zero, and the material is linear elastic. So I am writing it as in terms of E into Exx. Although you can use other hyperelastic models over here, but we are assuming that it is linear elastic. So if it is non-linear elastic, let's say hyperelastic material, so then this will be Sxx would be derivative of strain energy density with respect to Exx. So for the timing, I just said at the beginning, I wanted to demonstrate this for linear elastic. So I have said here linear elastic rod. So for the linear elastic rod, you will have this relationship in this form.
Okay, sir. So, like for linear elastic material, we used to have sigma is equal to E epsilon, like sigma.
Yeah, so now we are saying in terms of second Piola-Kirchhoff stress tensor is equal to Young's modulus into say x component of green Lagrange strain tensor.
Okay, sir. So it is also true in this case.
Yeah.
Okay. Okay.
That is what we actually use, although you could say some E dash, because this is referred to the reference configuration, but in the most of the time we end up using the same Young's modulus, which we get know from the UniXL test. So that is why I said it as E.
Okay.
And if you have nonlinear elastic material, so then this will be derivative of let's say hyperelastic material, so derivative of strain energy density function with respect to Exa.
Okay, sir.
Yeah. So now let me take another example. So this is one example. Let me take another example.
Sir,
So yeah,
sir, in the above expression which you have right now,
yeah,
so the whole part on LHS which is multiplied by delta D I plus 1, that is kg EI, right?
yeah.
Okay, means it includes the first integration also. Integration A B
Yeah,
plus BNL
integration.
transfer.
No, this kg I am saying only this one. This is separate. This one is
Okay.
separate. Kg I am only saying just this matrix. This matrix. This one.
Okay, sir.
Not this.
Okay, sir.
Yeah. So yeah, I think so. This is a matrix, and I know if you want to write in a Sartor form, so the way we wrote for the general case, you can write it as KTE at the ith iteration into delta D at the current iteration, that is I plus 1 is equal to FE, and for now you can see that KTEI is nothing but integration. So same thing, v 0 to L, you can say we can write E anywhere because it is a scalar. So we will have B plus BNL transpose into B plus BNL dx. This is evaluated at previous iteration, and plus we will have the second kg matrix, so that is integral 0 to L, and you can say sxx into A equal to n axial force, so you can write that as n, and then you have dn1 by dx, dn2 by dx into dn1 by dx, dn2 by dx evaluated at previous iteration. So this is KTE, and your FE. So you know that FE is the already the what we have on the right hand side. So minus we have A, know the integration over 0 to L, then A B plus BNL transpose into SXX dx I, and plus integration 0 to L H transpose Q dx, and plus we will have this minus Q1 and Q2, and then of course you need to do the assembly and whole of the solution steps. So I think let me write rather than taking the first next example, let me write this whole how the solution steps would be. So let me kind of write the solution procedure. So the solution procedure is that we will start with an initial guess. So usually we apply the load incrementally and start with the zero load. So for the next load step, we take the initial guess as the null displacement. So I'm taking this d naught. I think let me write naught outside. So d naught I is a null vector, and then now for ith I plus 1th iteration, for I plus 1th iteration, how will you proceed? So you need to first calculate du by dx, because that is required in sxx what is appearing. So no, of course you have to work out BNL matrix also required du by dx. So you will calculate du by dx corresponding to previous iteration for which the solution is known. So we will calculate this dn1 by dx, dn2 by dx, into DE evaluated at previous iteration, known at previous iteration. Once you have this, then you calculate B and BNL. So B of course is independent of D, but BNL would be calculated at previous iteration. And then once you have calculated this, so then you can calculate basically SXX. So SXX at the previous iteration will be Young's modulus E times the strain, so which is du by dx plus half of du by dx whole square, and this thing is evaluated at previous iteration. And once you evaluate SXXI, then you calculate KT, total tangent stiffness matrix. This KT is the total tangent stiffness matrix as I have defined already. So then you calculate this, and this of course for this problem you can do the direct integration because gradients are constant within the element, so you can easily do the integration. But if it is a problem where dn1 by dx and dn2 by dx are functions of say capital X or the natural coordinate xi, then you can also use Gauss quadrature numerical integration if required. In this case it will not be because all the gradients are constant, so you can actually use the direct integration, explicit integration. So you do this, and then and I think one more quantity which is to be calculated, which is should be there, is this axial force, where n is axial force. N is I think I forgot to define over. I have used n over here. This n. So no, the n is here. N is axial force, and this is equal to basically A into SXX. So you also need to calculate this axial force, which would be equal to A into SXX I. And once you have this, then you calculate your load vector Fe, and then now you basically assemble the element level governing equations and impose the boundary condition. Next step would be assemble the element level governing equations and impose boundary conditions. So that is one. And once you have done this, then you will solve for delta D. Now this is the global incremental displacement vector I plus 1. And once you have solved for this, then you solve for D at I plus 1 would be equal to D at I plus delta D at I plus 1. So after you solve this, then again go to each element and you will extract element level degrees of freedom, and then you do all the calculations and continue the solution. So repeat the above steps till solution converges. Repeat the above steps till solution converges. Yeah, so and of course as I said, for the all nonlinear problems you apply the load incrementally because you want to have the smaller steps, because your initial guess would be close to the solution for the first iteration. So if we take the full load, it will not converge because Newton-Raphson converges only when the initial guess is close to the actual solution. So that is why you have to divide the total load into a number of steps and then solve the problem. So here then increment the load and continue iterative solution. Increment the load and continue iterative solution. Yeah, so this is the whole steps. Now as you see, this is how the whole thing is done. Now let me take another example. So first example I took for this, the second example I'm going to take and like that. No, I think these are the two examples I'm going to discuss, and you can extend it for the plane stress strain problems, or you can extend it for the plate bending problems in a similar manner. The approach would be similar. So because I will not be able to discuss all the examples, I can only discuss few examples. So second example, I am taking this linear elastic Euler-Bernoulli beam. So this is the second example I am considering. Again, I will only discuss about the element level governing equation. So let us say you have the beam element, and this is the x coordinate and this is the y coordinate, and the beam is subjected to this distributed transverse load, that is q, and this is node 1, this is node 2. The length of the element in the initial undeformed configuration is small l, and when this deforms, so this deformed element is, let us say, like this. This is the center line, this is the center line here, and if we take any line element, let us say this line element, so this line element goes over here. So this is the line element, this was the original state configuration of that line element. And so now if you see the center point of this line element, which was here, it gets displaced by an amount u naught. So this is equal to, this is u naught. And if you see here, this a small this displacement, that is y times dv by dx in the Euler-Bernoulli beam element. So then what you do, you write the displacements. So as per the, now we have to, for the finite deformation, we are also considering u naught. Otherwise in the Euler-Bernoulli beam node under transverse loading small deformation, you don't consider u naught, but for finite deformation we have to consider u naught, because the middle the neutral surface or the middle surface would actually stretch. So now u of xy, which is a function of x and y, is written as u naught x. So u naught x is the displacement of the center point, and then the point at a distance y, so the point, say somewhere here, goes to here, so that moves by a distance of minus y into dv by dx along the x direction. So the total displacement is this, and v of course is taken only function of actually only x. So this is the displacement field. Now when we look at the Green Lagrange strain tensor for this, so we write exx. So only non-zero component of stress here is again sxx, and the corresponding strain is exx, because of course because of the Poisson's effect, eyy and ezz will also be there, but independent component of strain is only exx. So that would be equal to del u by del x plus half of again I am writing the Green Lagrange strain, so that is del u by del x whole square plus del v by del x whole square. Now actually this term, for most of the when the displacements, transverse displacements are of the order of thickness of the Euler-Bernoulli beam element, so for this term would be negligible. So the dv by dx is finite, but del u by del x is still small, so its square can be neglected. So this is negligible. So if that will be based on this assumption that du by dx square is negligible, we can
What is the
approximate.
reason, sir? What is the reason, sir, you said?
The reason is because axial stiffness is much larger compared to bending stiffness, so du by dx would be much smaller. Of course, if it is significant, then you have to include both. But I am discussing the case where du by dx is negligible. So reason is that its axial stiffness is quite high compared to bending stiffness. So the du by dx would be small. And that typically happens when the transverse displacement, bending displacement of the beam is of the order of thickness of the beam. So then no, you can write this Exx as now du naught by dx. No, u naught is only function of x, so I am writing total derivative minus we have y times d2v by dx square. This is the linear term, and only nonlinear term would be half of then dv by dx whole square. So this is the strain displacement relations you will have. And again, I am assuming that it is linear elastic. So you will see that the x component of second Piola-Kirchhoff stress tensor Sxx will be equal to E times Exx, and which will be of course E into du naught by dx minus f. Let me write all the terms. So minus y times d2v by dx square plus half of dv by dx whole square. So this is the x-axis. Now I want to we want to ultimate aim is to derive that incremental form of the element level governing equation, so that we can then solve the problem subsequently. So now if you let me rewrite the expression for Exx. So Exx, I want to separate out the cross-sectional coordinates. So you can write it as 1 and minus y as a row vector, and then you have a column which is involving this du naught by dx plus the terms which are the multiplying with unity. So we also sometimes call that as a membrane strain. So half of dv by dx square, this I am keeping together, and then the second term is d2v by dx square, that is curvature, that I am keeping it as separately. So in this the first one, this term I am calling as epsilon m, and this I am calling as epsilon b. That is epsilon m is the membrane strain and b is the curvature.
Sir, what is membrane strain, sir?
Membrane means which is independent of the cross-sectional coordinate. So it is the strain of the neutral axis, as you see over here. It is if you look at the Exx expression, so it has two type of terms. This du naught by dx plus half of dv by dx square, which is without the involving cross-sectional coordinate. Whereas the second term, if you see, it is minus y into d2v by dx square. Y is a cross-sectional coordinate. So this part of the strain is varying along the y direction. So that is referred to as bending strain, and the one which is independent of y coordinates of these two terms, these are referred to as membrane strains. So membrane means is kind of uniform, independent of y coordinate, and bending means it is dependent on the y coordinate. So along the y direction there is a linear variation of strain. So that is referred to as bending strain.
So can we say the membrane strain is in plane strain?
Yeah, it is. Both are actually in plane strain only. This both the components are the strain along the x direction, but one part, the first one is independent of y coordinate, and second one is linear function of y coordinate. So the one which is independent of y coordinate, that is referred to as membrane. Of course, it is in plane along the x direction. Both are giving the total, contributing to total strain along x direction.
Okay, sir.
Yeah. So now based on this, you can write this Exx. So these are some terminology we use in the bending, membrane term, bending term, and so on. So we'll have 1 minus y, and the first one I'm calling as epsilon m, and second one I'm calling as epsilon b. And so now if you look at from this, you can say the variation of Exx would be 1 minus y into delta epsilon m and delta epsilon b. So now for this, if you look at the element level governing equation, again only non-zero component of actually the strain is if you look at, so the non-zero component of strain is going to be only Exx independent component of strain. So now if you want to write the element level governing equation. So let me first give you the approximation of u naught and v. So approximation of u naught and v. So u naught we are going to interpolate using the linear interpolation function. So n1 into u naught 1, that the way we did for the no trace element, n2 into u naught 2, and here n1 is same 1 minus x by l, and n2 is x by l. But no, this v, because that involves no, in the equation you have v and dv by dx, so we want to have both v and dv by dx as degrees of freedom at the the nodes. So there are total 4 degrees of freedom corresponding to v. So we will use Hermite interpolation function. So v will be equal to h1 v1 plus h2 into dv by dx at 1 plus h3 v2 plus h4 into dv by dx at node 2. So here hi's are Hermite interpolation function. So I think you would know this is Hermite interpolation function.
So it means each node has 3 degrees of freedom.
Each node has 3 degrees of freedom, yes. U naught, v and dv by dx. Hermite interpolation function. So now if you look at, we want to identify the B and B and L. So now that I'm going to do with this delta of epsilon m and delta of epsilon b. So if you look at these two strains, so as per the definition, this would be delta of du naught by dx, and the second term is half of dv by dx square, so its derivative would be dv by dx into delta of dv by dx, and the second would be simply delta of d2v by dx square. So this is delta epsilon m, delta epsilon b, and this you can actually write it as the linear terms put together. So this is linear term, this is linear term, so that we want to separate out. So delta of du naught by dx would be equal to dn1 by dx 0 0, dn2 by dx 0 0, and then the degrees of freedoms are going to be delta of u naught 1, delta v1, delta of dv by dx at 1, and then delta of u naught 2, delta of v2, delta of dv by dx at 2. So these are the degrees of freedom. And the second term we will have delta of d2v by dx square, so that would be d2h1 by dx square, d2h2 by dx square 0, d2h3 by dx square, d2h4 by dx square. So that's the linear part, and this is the nonlinear part. So when you write the nonlinear part, you will have plus again the nonlinear part of the strain displacement matrix. So in the first term we have basically this dv by dx into delta dv by dx. So dv by dx we want to keep as it is, and delta dv by dx we want to expand in terms of the degrees of freedom. So let me write a little bit below that. So you will have here, it is only v, no, we have here only the v term, so 0, and then we will have dv by dx dn1 dh1 by dx dh1 by dx, then again dv by dx into dh2 by dx, then again 0, and then we will have again dv by dx into dx and dv by dx into dh4 by dx. So this, and in the second, in the epsilon b bending strain, we don't have any nonlinear term, so all these terms are actually 0. So these are 0, and this side of course you have again same delta u naught 1, delta v1, delta of dv by dx at 1, delta u naught 2, delta v2, and delta of dv by dx at 2. So yeah, this is what you have the the variation of strain So let me define this as basically B, and this as BNL, and this as delta of DE. So finally you can, as you see, this whole thing can be written as basically delta epsilon M, delta epsilon B can be written as basically B plus BNL into delta of DE. So this is what you can actually write this. So then after writing this, then you can write the element level governing equation for this problem. Element level governing equation. So the element level governing equation will be then the integration over 0 to L, integration over the cross sectional area. L is the length of the element in the reference configuration. A is the cross sectional area of the the cross section of the beam in the reference configuration. And then here we will have B plus BNL transpose, and additionally we have now this y was there. So when we are taking the transpose of the strain, so y transpose becomes the strain delta epsilon M and delta epsilon B transpose comes first, and when we take delta D out, so we get B plus BNL transpose over there, and then you have 1 and minus y will be here, and then Sxx the stress component along the x direction, second Taylor Kirchhoff stress tensor dA dx, and minus integral 0 to L, and then delta. Yeah, so now we will have V is equal to, now if you look at the V, so V term is basically, let us say, write the corresponding interpolation as HV transpose into Q dx, and then you have minus the internal load vector. I am just writing that as F1E, which would consist of axial force, shear force and bending moment at the two nodes. That would be the internal force, and this will be equal to a null vector. So this is going to be the element level governing equation. So here, pardon?
Can you please explain the first term of this expression?
The first term, actually, if you look at this term, we have if you look at in the variational form, so we have delta of Exx transpose into Sxx, isn't it? So basically, if you look at this term is integral 0 to L. So let me do that. So integration over area, and here you have delta of Exx transpose into Sxx and dx dA. That's what you have, right? This you agree, isn't it, that first term is because we have only one non-zero component of stress Sxx, so the virtual work of stresses is going to be delta Exx transpose into Sxx, and then delta Exx transpose is, now if you look at, it is written as integral 0 to a integral over a. Delta Exx is now written as delta dE transpose, and then you will have B plus BNL transpose, and then you have this matrix 1 minus y. Why this? Because if you look at this strain, what I have wrote here, here, this is your delta Exx, which is 1 minus y into delta epsilon M and delta epsilon B. When you take its transpose, it would become delta epsilon M delta epsilon B transpose, and then transpose of this, so it will become a column vector 1 minus y. So that is what is written here, delta D transpose into B plus BNL transpose into 1 minus dy into Sx dx dA. And then now you take delta D is arbitrary, so you take that out and then write rest of the term. So that is how you get this term finally, which I have written over here directly. So is it clear?
Yes, yes, sir.
Okay. So yeah, so this is something intermediate explanation. So now if you now once you have this, so then we have to look at the, I think I have the one thing which I have not defined is HV. So if you look at the delta V, that would be 0, H1 H2 0 H3 H4 into delta DE, and this I am calling as actually no HV, this matrix which I have used over here, into delta D. So that is delta V. So now if we have got this as the element level Gaoni equation, I know this one. Now we want to write the incremental form of this. So if we want to write the incremental, I think, can I take 5 minutes more?
Yes, sir.
So yeah, so now if you look at the incremental form using Newton, now again if you look at this equation is a nonlinear equation. No, if you look at this equation, the element level Gaoni equation, it's nonlinear because no BNL contains dV by dx term, and Sxx is of course containing du naught by dx and dV by dx square terms. So it's a nonlinear equation. So to solve this, we need to use Newton-Raphson method, and for that we write its incremental form. So the incremental form would be, incremental form is going to be basically the increment. Now if you look at here, so first we have to take the increment of Sxx, no, so there are two terms, and this side also we have to take the increment of BNL. So the increment of both these terms have to be taken. So therefore when you write this in the incremental form, it is similar to the previous case we did. So integral 0 to L integration over the cross sectional area, and then you will have B plus BNL transpose, it is as it is, and this 1 and minus Y we have as it is, and then we are writing delta Sxx, and delta Sxx I am writing E into delta Exx, and then delta Exx is written as in terms of cross sectional coordinate and delta epsilon B and delta epsilon M. So we will have Young's modulus E here, and then 1 minus Y. This is not 1, I mean it's a column, it's a row matrix. So this is 1 and minus Y, and then we will have delta epsilon M and delta epsilon B. So that can be written as B plus BNL, and then integration over dA dx. This whole thing is evaluated at previous iteration, and then here you will have delta DE for the current iteration. So that's the first term. And then the second term again is going to be integration 0 to L integration over cross sectional area, and then we will have delta BNL transpose, and then 1 minus Y is there as it is, and then we have Sxx which is evaluated at the previous iteration, and then we have this dA dx. So these are the derivative terms, and then plus we will have now this integration 0 to L integration over cross sectional area, and then we will have B plus BNL transpose, and 1 minus Y, and then you have Sxx, and then dx dA. This is evaluated at previous iteration, minus integration 0 to L. We will have this HB transpose Q dx, and minus we will have this internal load vector, and this is equal to a null vector. So this is the incremental form. Now what you can actually do is no, you can take now if you look at basically this term, this here. So this will be a 2 by 2 matrix. When you multiply 1 minus Y column vector with 1 minus Y row vectors, it would be a 2 by 2 matrix, and then you carry out the cross sectional integration. So integral basically EDA would be E into A, and integral EY square DA will be equal to E into IZZ, and integral Y DA would be 0 because we are assuming that neutral axis is at the the geometrical centroidal axis of the beam. So now you can actually write the first equation as integration 0 to L, and the cross sectional integration is already done. So we will have B plus BNL transpose, and then as I was saying, this would be EA 0, and this would be EIZZ, and then you have B plus BNL, and then dx. This whole thing is evaluated at previous iteration into delta DE evaluated at current iteration, and plus the similarly the second term. If you look at this term, so we keep this as it is. Integral Sx dA would be Sx into A, that is axial force M, and integral minus y Sxx minus y Sxx dA, Sxx into dA is force, into y is the moment, and minus y will give you the basically bending moment. So you can write it as integration 0 to L, and then you have delta B NL transpose into, as I said, the integral 1 into Sxx dA is N axial force, and integral minus y Sxx dA is M. So we will get here M, and this is evaluated at the previous iteration, and this of course is evaluated at the current iteration into dx. So this will be the first term, the second term. Then the third term is integration 0 to L, and B plus BNL of course remains as it is transpose. And then again we have no here, if you look at 1 Sx, no, we had both places here also 1 minus y into Sx, Sxx, here also we have 1 minus y and Sxx, so that also will translate to N and M, so that is N and M dx. This is evaluated at previous iteration, minus of course external load vector, so HB transpose Q dx, and minus this internal load vector is equal to a null load. So you can write it like this. So now here if you look at, where now N is nothing but integration over cross sectional area Sxx dA, and M is a minus integration over cross sectional area y Sx dA, and A is the cross sectional area, which is integral A dA, and Izz is the integration over cross sectional area y square dA. So these are the definitions we have used. Now if you look at the essentially now if you look at the delta BNL term, so which is integration, because we want to write that, bring out the Kg matrix there. So we have delta BNL transpose into, you have N and M dx. So now what do? We want to take out delta D common in this. So if you look at delta BNL, only the first row is non-zero, the second row is actually 0. So when it gets multiplied with M, it would go to 0. So if you expand this, you can actually write this as integration 0 to L, and then delta BNL has got dV by dx and delta of dV by dx. So dV by dx we have in terms of dHV by dx transpose into N, and then we have delta of dV by dx, so that comes as dHV by dx, this matrix into dx, and this whole thing you can take right hand side delta D as a common term. So therefore finally you can the second this term you can see if you look at the expression for delta BNL, put the expression for delta BNL, multiply this, and finally take delta D common on the right hand side, so you can write it like this. So the final form of this equation, of incremental form of the equation, is basically your tangent stiffness matrix KTE evaluated at previous iteration into delta DE for the current iteration is equal to total load, elemental total load FE. So now where if you look at this KTE is basically equal to integration 0 to L B plus BNL transpose, and then we have this 2 by 2 matrix EA 0 0 EIZZ, and then we have B plus BNL into dx, and this whole thing evaluated at previous iteration, plus the geometric stiffness matrix part, so which is integral 0 to L, and then we have this dHV by dx transpose into, we have N, and dHV by dx. This is evaluated at previous iteration. So this is your KT is tangent stiffness matrix. KT is referred to as tangent stiffness matrix, and then your load vector is minus integration 0 to L B plus BNL transpose into NM dx evaluated at previous iteration plus integration 0 to L HB transpose Q dx, and plus you have this internal load vector. So this is the final form of the incremental form of the equation. The solution procedure would be similar to what I discussed for the Euler-Bernoulli beam, the truss element. So I think I want to stop here, and if you have any doubts and questions, you can ask. Yeah. So any
Hello.
doubt? Yeah.
Sir, like you said, there could be displacement in axial direction also U naught.
Yeah.
But like if we have a tensioned beam which is fixed at both the ends, so in
Yeah.
that case, do we need to consider this axial degree of freedom also, or
Yeah,
we can
even
neglect?
then you need to consider, because what will happen is, when it is both the ends, let's say, fixed, and you apply a transverse load, so you will see that when the beam deforms, so its curved length is going to be more than its initial length, length of the neutral axis. So length of the neutral
Okay.
axis in the undeformed configuration would be different from the length of the neutral axis in the deformed configuration. So you still need to consider U naught.
Okay. And
Yeah.
sir, like if we are considering it as a small deformation problem where we are not considering geometric nonlinearity, then
Yeah.
also do we need to consider?
No, then you need not consider that. You only if there is a only transverse load, then you just need to consider only V. You not will be will come out to be actually 0 even if you include for linear problem under transverse
Oh,
load.
okay.
Yeah.
Oh, okay, sir. Thank you, sir.
Yeah. Okay. So any other question, anybody?
And sir, there is one request, sir.
Yeah.
So can we have few more days extension for the assignment? Like we have submitted already, but like we were facing some difficulties. So is it possible, sir?
Yes,
Yeah.
sir. Please, can you please extend for assignment, sir?
Okay, so I think I can then extend to what, by Friday?
Yes, sir.
Okay.
So that would be a thank you,
Okay.
sir.
Okay. So any other question, anybody on this, whatever we have discussed so far? So I think if you have followed the general derivation, so these examples are just no specific theories and assumptions, and then how do we write those equations. So I think you should be able to follow, but no, you please go through the whole thing, and if you have any doubts and questions, no, you can ask. Oh, are there any other questions? Yeah. Yes, please.
Sir, can we have some practice questions? Actually, sir, what happened in the paper, like it was happening that like the writing speed was very slow because of lack of practice. So can you give us some sample questions?
Yeah, I think, see, yeah, I can give some questions, but the difficulty is because there are not actually all these problems is they're computationally so involved that most of these things have to be done through the computer programs. So actually anything in hand calculation is not possible. So what I can only ask in the exams is the some intermediate calculations and some simpler questions, the problems. So I have very limited freedom to give you the questions on these. So that is why we have these programming assignments where you learn how to implement these.
यस सर, एक्चुअली पेपर में वही हुआ था कि मतलब क्वेश्चंस आते थे बट मतलब प्रैक्टिस उतनी नहीं थी, तो मतलब कुछ क्वेश्चंस अटेम्प्ट ही नहीं हो पाए थे, तो वो थोड़ा सा इशू हुआ था सर मिड सेम के टाइम पे, मतलब
Yeah,
माइनर.
yeah, in this minor, yeah. So let me see. I think wherever possible, I am giving some examples. Like here, I am giving examples of 1D examples. So you should practice these kind of other problems, say plane stress, plane strain problems in a similar logic, plate bending problems in a similar logic, so you can practice.
Okay, sir.
Yeah. Any other question, anybody? Okay, so if there are no questions, I am stopping. Thank you all for your attention.